All right, let's get started. So very happy to have Vishrant Tripathi with us once again. I think a couple of years ago you were here. Vishrant is a young faculty at Purdue. Before that, he got his PhD from MIT. And today we're going to talk about age of information.
Thanks, Rahul and Abhishek and Raghuvansh for hosting me. It's always good to visit TFR. I did my undergrad up north at IIT Bombay, so it's always good to be back in Bombay as well. So what I'm going to talk about is 3 papers that we have worked on over the past 3 years. And they're kind of trying to plug in some holes that were remaining in wireless scheduling for age of information, specifically for trying to do monitoring over wireless networks for resource-constrained wireless networks. And so those 3 holes that we want to plug are distributed protocols, correlated sources, and non-uniform updates like this. So I think will become clearer as we go through the slides. And all of this work is in collaboration with a bunch of people. So some of it was done while I was at Lids at MIT during my PhD. Some of it was done with people at Northwest, and Igor Kadota, who is now a professor there from Eytan's group and one of his master's students. And now I'm affiliated with Purdue, so a bunch of different universities and different time periods. So let's get started. So I will try to introduce the standard setup and why we are interested in this problem and what exactly the mathematical problem is. So you have a bunch of sources. All of them are trying to send updates to a single base station. And the base station is interested in monitoring the status of all of these sources. You can think of these sources as some sensors that are trying to measure some process that is happening. And the goal is that you want to design a scheduling policy. Because there's interference or bandwidth constraints over this wireless network, not all sources can transmit at the same time. So you have to pick which sources get to transmit at each time slot. Let's think of a discrete time setup. And you want to design a scheduling policy. But what do you design the scheduling policy for? What do you want to optimize as a goal of the scheduling policy design? That's where we introduced this notion of age of information. A bunch of people have looked at age of information now almost for about 15 years at this point, starting from Colin Yates' seminal paper in 2011-12. The idea is, let's say that source 1 transmitted last 10 time slots ago. So the information at the base station right now for source 1 is 10. Similarly, for source 2, there's some level of information staleness at any given point at the base station. And so this level of information staleness for each source I at the base station at time t is what we will represent as AI of t. And that is the age of information for source I at time t. It's how long it has been since source I sent its current information to the base station. So how stale the information is at the base station at any given time for any source I. The weight of each information piece is Wi. It basically represents how important each source is to the overall application. So if you're trying to do, say, some real-time control, some of it is slowly varying information like temperature. Some of it is quickly varying information like position or some video information over which you want to do like real-time inference. That might have a much higher weight than, say, temperature. And so this encodes importance to the application. Given this kind of a cost function, you want to minimize the information staleness summed over time, subject to importance weights. And you want to minimize this over the space of all possible scheduling policies. And this is a standard optimization problem at this point. People have looked at many different variants. They look at different kinds of cost functions, different kinds of network constraints, different kinds of network setups, not just a single hop wireless network. And they have solved it over the past decade. Abhishek actually has a very nice paper on it together with Igor back in 2016 and 17.
So is it correct to say the inputs here are the weights and the output is the schedule? Or
so the input would be the weights, the number of sources, and the constraint that you would have. So here I kind of hand wave it. I say only a small subset of sources can transmit at any given time. In most easy versions of the problem, we will say one source can transmit at a time. You need to pick the best source in each time slot and design an infinite horizon scheduling policy. So that's correct. Yes.
But the information of the sources is not stochastic. I mean, you use some periodicity and it comes with.
So the information of the sources is kind of exogenous to the entire problem design. We assume that all of that has been modeled into this age of information. And so at any given point in time, if your age of information is high, then you are uncertain about the state of the source. If your age of information is low, you are more certain. And this is all that we care about. But really, you could put any time varying source in there. We kind of don't really care. We'll kind of get to that as being a drawback of some of this design, and if we can try to do something better. So this is the standard setup, and we actually know how to solve this. So the good is we know how to solve this problem, at least near optimally, through Lyapunov and max weight-based techniques. This is what Igor Kadota and a bunch of other folks from Eytan's group solved in 2016. And the general idea is that you basically design a policy that looks like, choose the source that has the highest value of weight times age squared at any given point of time. This policy will perform very nicely, and it has nice provable properties, and you can do some analysis to show that it has nice provable properties. There are some problems with this. The design policy, it needs to take a maximum over all possible sources. And it needs to know the age of information of all sources. So it needs to be centralized. You need this base station to pull information from these sources. So it's not like an 802.11 protocol or a Wi-Fi protocol based on CSMA, where they can decide when to transmit just based on their local state, right? So they're not distributed. The second is, throughout a lot of these scheduling papers, there's a central assumption, a simplifying assumption for analysis, which means that to transmit a packet from each source to a base station takes one time slot. And this one time slot is fixed for all sources. But in many settings, you might have a camera sending video frames and say someone sending audio frames and a robot sending GPS information. These are very different in packet sizes or update sizes for your application. And so this is not really necessarily a practical assumption. It is a nice assumption for analytical simplicity, but practically it might not hold true. So we need to take account of both of these realistic kind of issues with the policy design initially that was proposed. And then the third, which, as you kind of mentioned, age of information is only a proxy for the real application goal of, let's say you want to minimize monitoring error under some kind of assumption on how this source varies over time, some stochastic or temporal assumption on how the source varies. It's not necessary that minimizing AoI will actually lead to minimizing monitoring error or application performance cost, especially if the way these sources are varying are also coupled across these sources. So throughout this assumption, you assume that if source I transmits, then only the age of information of source I drops. If source J transmits where I is not equal to J, it does not influence any of the other sources. But if what you're doing is monitoring a system of cameras that have overlapping fields of view, and you look at an update from that camera and an update from that camera, they have some overlaps. And so if I hear from that camera, I also know something about the state of the area that this camera was monitoring. And that is not really captured just in the AoI table. And so that is also something that we will try to address in one of the papers. This becomes very tricky because how do you define correlation? How do you measure correlation? All becomes very tricky. So we will give some partial answers to this. This is, I think, a more general and harder problem to solve. The first two are slightly easier to solve, which is how to design distributed policies and how to take care of non-uniform packet sizes. We can still do it through the usual Lyapunov tricks and techniques. The second part is slightly trickier. Okay, I'll stop here for questions at this point. So the basic setup.
What is your channel model?
Channel model, I will assume throughout is one source at a time. For packet sizes, when I handle non-uniform packet sizes, I will assume that you know channel reliability, Bernoulli reliability over time, P1, P2, Pn. For the distributed policies, I will assume reliable channels. And for the correlated setting as well, I will assume reliable channels. So I will not even handle.
So you're assuming that you know the probabilities.
Yeah.
You are not estimating the channel. Right?
Yeah, I am not learning anything. Yes, that is correct. Okay, so the talk will have 3 sections. Each of these will address 3 of the questions that I have raised. So the first will be, what I'll try to do is distribute the centralized protocols that we know solve this problem optimally. So I'll just consider the vanilla version of the problem, but design distributed policies with nice performance guarantees. The second one will try to look at correlated monitoring. How do you model correlation in a monitoring scenario? We give a simple answer. And then given that correlation structure, can you design policies that are optimal for monitoring error and actually show that they will be very similar to policies that minimize age of information? So AoI is approximately equal to error. It is a good proxy in certain settings. And the third one will be where you have diversity in source update sizes. Some sources send very large updates, like camera or LiDAR sensors. Some sources send very small updates. How do you design a policy that accounts for these differences? So these are the 3 main topics that we will cover. Let's start with the first one, which is what I call fresh CSMA. So this is our protocol which is a take on CSMA, carrier sense multiple access, which is a well-known distributed protocol in wireless networks. It is basically the backbone for all Wi-Fi. So what we want to do is modify CSMA so that it can optimize for age of information. Normal CSMA mostly just optimizes for throughput and has some nice robustness properties, but it doesn't really optimize for age of information. So let's first go back to our original age of information optimization problem. We want to solve this. And what Igor Kadoda and a bunch of other folks showed was that a max weight style policy works to solve this near optimally. And the policy does this. At any point of time t, find the source j that has the highest value of weight times age squared. This roughly says this is the source that is the most stale, and transmitting that source will give you the most valuable information right now to minimize this overall system cost.
But this assumes that the channels are identical.
Yeah, right now I'm assuming channels are identical and reliable. So throughout section 1, assume that P1 up to Pn equals 1. No unreliability. So for this, what I'm trying to show for section 1 is that even for this setting, right, you need a centralized base station to run this policy, to compute this argmax. And what I want to do is distribute this argmax computation without needing a central base station using a CSMA style approach. So that is what the goal will be. You can extend the general idea while having unreliable channels and the general analysis will hold. For simplicity, I won't do that. Make sense? Okay. So what we know is that this policy is actually guaranteed to be at most a factor of 2 away from the optimal scheduling policy, which you could run by running dynamic programming over an infinite time horizon, which is extremely computationally involved and has the curse of dimensionality. So you would never do that. This policy is computationally efficient and has nice optimality properties. What we want to do is have a similar policy that has the same optimality guarantee, but is not centralized. It does not need to know at each source what the age of information of every other source is, and it does not need a central agent to compute this argmax.
So only the source the source decides when to send.
Yes, each source will decide when to transmit.
So what can you assume that all the sources have some common source of randomness or something?
You don't need that. Yeah. So that's kind of the nice thing about how we do this. You don't necessarily need common randomness. You do need randomness. That is kind of the core of CSMA. And so that's where we will kind of start. So we'll start with the basic CSMA-CA protocol without any age of information changes to it. In the most simple setting, what happens is that a wireless frame starts. At each source, the following flowchart happens. It senses the channel and checks if the channel is idle. If the channel is idle, it just starts transmitting. If the channel is not idle, it basically generates a random number. It waits for that random number and then tries to sense the channel again. And basically, if it keeps sensing the channel as busy, it will not transmit. So that's why it says carrier sense multiple access, and the CA is basically channel avoidance. So it avoids the channel whenever it senses that the channel is busy. And this seems to work pretty well in a lot of practical systems. It is the backbone of Wi-Fi, as I was mentioning.
Usually there's some exponential backup, right? That you're not kind of.
So usually, I have said it wait for a random backup timer. If you're doing things in continuous time, the nice way to model it is that you say, yes, the random backup timer will be an exponential random variable. So we will actually do that soon. Yes. And this general kind of approach has been studied by a bunch of people, and its properties have been analyzed for queuing networks.
It's the same backup, like it's the same distribution. Like it's not,
Same distribution, but everyone will generate it independently.
it's not like the TCP thing where you keep increasing your backup time.
No, yeah, it'll be a fixed distribution that I'll sample from every time that I want to sample from, and each source will do it independently. Yeah. And so this has kind of been analyzed well for the throughput optimal setting by Jiang and Walrand in 2009 and Lee and Erlenmaz in 2013. What we will want to do is modify it for the age of information setting. So
does the sender know that the information was transferred successfully?
So acknowledgements. So there is no, if there is collisions, then you will need to retransmit, and you know if there is a collision that you will need to retransmit. So you will have access to acknowledgements, yes. Yeah. The nice thing with age of information is that if there is a collision, you will actually never retransmit the old information, you will just transmit the newer information. So you actually don't necessarily even need acknowledgements. But so that's why in our model, we don't really care about acknowledgements. If you were caring about throughput and drop packets, then you would need to know acknowledgements so that you need to retransmit. Yes. So this is the same picture, but on a timeline scale. So at the beginning of the frame, each source picks a random timer. And I'll just describe them as Z1, Z2, Z3, Z4. So think of 4 sources. Each of them picked a timer, Z1, Z2, Z3, Z4. What will happen is that while these timers are running, because the channel was occupied here, all of them will sense the channel at the beginning of the frame, say it was occupied, and start running a random timer. Source 1 has the timer that runs out first. Because it runs out first, source 1 will get the channel, and it will start transmitting. And it will transmit for the entire frame. And then the same thing will repeat again and again and again. So whichever one has the shortest timer wins the race and gets to transmit. And if 2 people have the same exact timer, then there's a collision. The nice thing is if you assume everything is in continuous time, that will happen with probability 0 and there will be no collisions. Of course, that's not practical, but for analysis, right now we will assume continuous time. And you will assume that these timers can be implemented with infinite precision. And so there will be no collisions. That's not true, but we will assume. And usually these are just exponential random variables with some fixed parameter, right? So this is standard CSMA still, very simplified model of CSMA. To replicate max weight, we will just tune the way in which you are sampling your back-off timers. So what we will do is ZIFT, each of these back-off timers are now exponential random variables, but instead of having the same parameter across each source, your parameter will be some alpha to the power WI AI squared. So the larger your age of information, the higher your exponential parameter. The higher exponential parameter, the faster it will run out because exponentials have a mean of 1 over lambda. Lambda is large, then it will run out faster. So basically, with high probability, if this alpha is large enough, the source with the largest value of WI AI squared will have the shortest timer. And if it has the shortest timer, you're done with the argmax because that will get the frame. So that is what we show. Basically, the scheduling decision is the source that has the shortest timer, the argmin of ZIFT. And the probability that source J gets to transmit during a frame is proportional to this parameter, alpha to the power WI AI squared. And these can be shown easily given the mixture of exponentials that you have. So the nice thing with all of this is the 2 results that we were able to prove is that per time slot at any given point of time, if your age of information states are the same, then if alpha is large enough, the probability that fresh CSMA, the CSMA protocol, will make the same transmission decision as the max weight protocol, which is centralized, is going to be large enough. So given any delta, I can choose alpha large enough such that this probability will be greater than or equal to 1 minus delta.
So this is soup over all t, right? I mean, for all t.
No, for any given t and any given age vector. So this is a 1 time slot guarantee, not a time horizon guarantee, 1 time slot guarantee. The next result states, over a long enough time horizon, if I take the time average, my fresh CSMA policy will be at most a factor of 2 away from the optimal policy. And this we show using Lyapunov drift arguments.
This doesn't assume that the age of information is discrete. Like
the age of information is discrete. Yes, we assume age of information being
the ratio there.
Yes, exactly. Yeah. And what you will notice from this time horizon guarantee is that this is exactly the same performance guarantee that Igor and Abhishek and all the people in their papers for age of information will have for centralized policies. So a performance guarantee for a distributed policy over an infinite time horizon is actually the same. And so we have achieved what we started out with, which is to say that this is a distributed policy with independent randomness. All you need to know is your own weight and your own age of information at any given point of time. And you'll get the same performance as that of a centralized policy. Of course, there were some very strong assumptions with that. So that is what I will list. Our backup timers are implemented in continuous time. I assume that carrier sensing happens instantly. So you can instantly sense the channel and get feedback. There's a frame-based system with perfect synchronization across sources. So there's no deviation in clocks between the sources. And the backup timers can be made arbitrarily small and precise so that there's no collisions. And the consequences are that there's no probability of collisions, and then there's no overhead. And by backup timer overhead, I mean, if you go back to this figure, while all these timers are running, this yellow part is when the channel is just empty. No one is using it, right? And that is an overhead. You are not using the system capacity. But if you make these backup timers all arbitrarily small, then you can shrink this period to be arbitrarily small and there will be no overhead. All of these are not actually practical. You work with discrete time and you work with finite precision and reliability for these systems. So how do we fix this? So we convert this into a discrete time system. what we do is now everything is discretized to mini slots, where there are frames that consist of a large number of mini slots, where mini slots are actually very fast. They can typically take 9 microseconds in Wi-Fi. And that is the basic amount of time you need to sense the channel and check if there is power in the channel, if someone else is transmitting or not. So your basic unit of time is mini slots. In most Wi-Fi, you're actually synchronized up to 1 mini slot. So each source that is connected to the same Wi-Fi router will be synchronized up to 1 or 2 mini slots. So there's good synchronization. The frames for which you're transmitting the packets actually take a long time. So they'll take usually milliseconds or order of milliseconds to transmit a kilobyte sized packet. And we will discretize the timers to be integral multiples of these mini slot lengths. So instead of having now continuous time timers, we'll have discrete time timers, which we'll call D1, D2, D3, and D4. So ZIT is still sampled as I would have done before, but using this kind of discretization with 2 parameters B and beta. I take the logarithm of ZIT, I take the lowest integer function, I add it to B and do a maximization to ensure that I get a positive or non-negative number. Not really important why I do this, but I need to do some kind of discretization and I need to do it in a reasonable way so that these timers don't run off too far. That's why I do the logarithmic, and the B is just to adjust it back to a positive number. But once you have discretization, there are 2 things that happen. 2 sources can choose the same mini slot timer. So you get positive probability of collision. And then the other thing is that all of these timer lengths are positive. So you will get positive back-off overhead. So there's a significant overhead for when you implement your distributed policy. So what you might have thought from the beginning of the talk is that you get all of this for free. That's what our analysis shows. You actually, in practice, cannot get distributed protocols for free. The cost of distributed protocols is this collision probability and the back-off overhead, which I was hiding in my idealized analysis. And in our paper, what we do is we explore this trade-off and we show how do you choose these parameters B and beta, and how do they affect your collision probability, how do they affect the back-off overhead. That analysis is slightly more tricky and not as intuitive, and we actually don't have closed-form performance guarantees for this near realistic discrete time models.
So does it depend on the number of sources that you have?
It will also depend on the number of sources.
But that is not known, right? Because
we assume for our analysis that you know, but in typical random access networks, you might not. Especially in a distributed protocol, you might actually not know. But if someone asks me, I give you B, beta, and N, can you tell me what the collision probability would be? I'll not be able to give you the collision probability, but I'll give you an upper bound on it. And if you ask...
any.
Yeah. But with reliable channels, yes.
Yeah.
Yes. So I can give you what would be the collision probability, assuming everything else is not good.
And what happens in the continuous time model?
The probability of collision is 0 because you can just make everything arbitrarily small.
Okay.
Yeah. So that's why this is more realistic. It's still not completely realistic because channels are reliable. But as long as, let's say, for most Wi-Fi scenarios, if you're within like 2.4 gigahertz and there's no other interfering network, everyone is on your network, then channels are pretty reliable. So you get away with the analysis. So yeah. And we can also analyze back-off overhead. Again, analyzing exact back-off overhead is tricky, but we provide some nice analysis on upper bounds for the back-off overhead. And we can characterize, given B, beta, and N, and the weights of age of information, what would your back-off overhead look like? So how much overhead do you pay for this distributed protocol to be distributed instead of centralized? That is the loss in capacity that you get from these gray periods instead of the blue periods.
So in this frame, we are looking at things. If someone sort of like if one of the sources senses at a very late time in the frame, and
so yeah, in this near realistic model, I'm still assuming synchronization of clocks across sources. That is one thing that I do not address. Everyone is going to start here at the same frame. So I say frame T begins for each of these sources at the same time. Good point.
Yeah, so they will know that they cannot, so they will not even.
Yes. So if you have this asynchronization, then things become even trickier. The nice thing is, at least in 802.11, that you'll be synchronized up to 1 mini slot. So if M is large, then you are going to be mostly synchronized within this frame boundary, close to the frame boundary. But that really depends on your practical implementation.
Yeah. So which parameters alpha, B, and beta, like what do they depend on? So it depends on the number of
yeah, so we show, for example, that our results depend on, say, for this slide. Both of these results depend on alpha being large, right? I say if alpha is large enough, these two results hold. I kind of hid what the dependence on N is. for proving these results, I actually need to choose alpha very large. I need to choose alpha to grow linearly, sometimes quadratically with n.
But is it just n or is the sum of the weights? Or?
It can depend on the weights as well. Yeah, it will depend on the relative ratio of weights because you can always take the ratio and increase. So yeah, but the nice thing is practically you actually don't need alpha to scale with n. So I'll show with simulations. So to prove it, I need alpha to be large.
Okay.
But so this is the first simulation. In this, what we do is we plot weighted age across the network size. I'm plotting a few different policies. The blue policy is the optimal stationary randomized policy. So this is roughly a policy that is centralized, but chooses each source with a fixed probability. So it will choose source 1 to transmit with P1, source 1 to transmit with P2, source 3 to transmit with P3. And we'll compute these probabilities optimally by solving a convex program. And we can do that, and we know how to do that. So that is the blue policy. It doesn't really perform very well, even though it is centralized. The blue dotted line without any squares is the centralized max weight policy. We know that it is nearly optimal and performs very well. On top of it is the red line with the triangles, which is the idealized CSMA with no collisions and all of the assumptions that we had on the idealized kind of collision model. And we see that it almost exactly matches the max weight policy. There's essentially no deviation. And the near realistic protocol is where you see kind of the extra cost of distributing this policy, which is that there is still some gap, and that gap comes in because there are some collisions, because there's some overhead in our protocol, which shows that, sure, we can replicate the centralized policy, but at some cost, because we are doing it in a distributed.
Sorry, why is it useful to also compare them to this optimal stationary randomized?
We wanted to do that because it is a centralized policy that does not really do the argmax computation. It just picks probabilities at random. And we wanted to show that this kind of argmax is really necessary, right? So that stationary randomized policy can be easily randomized and it can easily be distributed. Each source can kind of just decide to transmit with a fixed probability, and it is easy to distribute, kind of easy to handle collisions as well in CSMA. But
the channel is identical. The channels are identical. So I don't see like why anything other than a uniform distribution is going to be useful here. I mean,
for the optimal stationary randomized,
optimal stationary
weights, right? You'll
weights.
square root of weight.
Okay.
So you'll have
I see. So if weights are all the same,
then you'll just do 1 over.
I see.
Yeah. That's what like AoI basically. But centralized, it will not be like AoI. But if you wanted to distribute that 1 over n policy, you will do something like AoI. So each one tries to transmit with 1 over.
I mean, that will be okay. So if you have weights and problem, guessing that is going to be proportional to the weights.
Yeah, square root of weight.
Okay.
Yeah. The standard like ego standard result. Yeah. Yeah. So this is the first simulation result. The second one, as I was mentioning, was that we have these results that say, oh, this holds for alpha that is large enough. But what I want to show is, I have that plot. Okay, I don't have that plot. But if you go into our paper, you will see that you don't really need alpha to be large enough. For a lot of settings, as long as your frame length is large enough, the capital M is large enough. So you're sending large packets and not small packets. Your alpha can be 2 or 3, and you're taking these powers of the weight times age of information squared, and you will get pretty good performance with this distributed protocol. So you can actually just hard code this parameter into your Wi-Fi router, and as long as you change the way in which it is sampling these exponential backoffs, you will get very good performance. So one of the things that we want to do with this is eventually kind of implement this with software-defined radios and see what kind of good performance we can get compared to a off-the-shelf Wi-Fi router. So
yes, but this will depend on n, right? I mean, you can't just.
So that's the nice thing. The alpha can be kind of, at least empirically, it does not need to depend.
Oh.
Theoretically, for our proofs, it does. For simulations, it doesn't. And so
what alpha you use in practice?
For most simulations, I think I had set it to 2.73. It works out like just a fixed factor for all of this, varying from like source 1 to source 85. Didn't really matter. It worked out pretty well.
So why is it happening in practice when is that an exponential?
Yeah, because it's exponential of exponential, right? So it's like
okay.
So it's like 3 to the power of weight times age squared. As long as the age is large, it will work well enough that you will get good convergence or like good. The timer will be small enough that you will get good decisions. And if your decision is like slightly off over a long enough time horizon, it doesn't impact things. So instead of, because you're trying to do argmax, right? If instead of picking the maximum, you pick the second maximum sometimes because your random sampling was slightly off, it will not be a huge penalty. So that's kind of the rough insight. But for proofs, because you're trying to replicate the max weight policy exactly, you need alpha to be large to provide the theoretical guarantee. Make sense?
Yeah.
Okay, so I'll switch gears to the second problem. This is a slightly more challenging problem. And the way I try to motivate it is all of the prior work on age of information looks at sources that are completely decoupled. So each process, as I initially described, each camera's video stream is completely apart. There's no overlap. If source I sends an update, there's no gain for source J. If source J sends an update, there's no gain for source I. But that is not really true in practice, especially in a lot of these kinds of visual or robotics kind of settings where some sensors will give you partial information about other sensors. So solving this problem actually requires two different kinds of tasks, especially when there is correlation structure involved. So the first one is how to do estimation. So if someone tells you what the correlation structure is, and I give you partial information, even without designing the scheduling aspect of it, you need to figure out, well, given this past information and correlated updates, what is the optimal estimator? Because I need to learn or understand or know the correlation structure and figure out what my state is going to be in the future or do some prediction given this partial information. And the second is the scheduling, which is which source should I observe at any given point of time. In general, these problems are tightly coupled, which means that optimal design needs to look at estimation and scheduling together and not separately. For a lot of the age of information stuff, we assume that estimation is going to look like age of information. So the higher the age of information, the higher the estimation error. And so you can just look at the scheduling problem and assume that someone else has already designed the optimal estimators. Once you have correlation, that is not true. There's some control and monitoring papers that established this in like about 20, 30 years ago. So the general problem is tightly coupled and hard to solve. Yes.
So what again is the state here encompassing?
Yeah, so I have not really described that yet. I will describe that soon. For our particular case, we will actually assume that the state is simply a Gaussian random walk in discrete time. So something that is very easy to model, for which we actually know the statistical model. But in general, things could be very arbitrary. We don't really deal with the arbitrary case of how you define correlated kind of sensors and sources in general. We will define a very specific model and then try to solve it, which is primarily designed for analytical ease rather than practical applications. So what we will show is that for our particular case, there will be some decoupling. So you can design optimal estimation, and given optimal estimators, you can design optimal scheduling policies. And what we'll show for our particular problem, because it's an LTI system with Gaussian random walks, the optimal estimation will look like a Kalman filter. And the optimal scheduling will look like some kind of dynamic program that you need to solve subject to the optimal Kalman filter. And so they will decouple nicely, and then we can solve each piece independently. And one piece is something that is very well known and has been well known in the control community now for 56 years. Yeah, you can think of it like that, but MITR mostly considers things like rate constraints rather than like interference constraints, so slightly different style. But motivation is very, very similar from them. Yes. So our system model is still the same. We have a bunch of sensors trying to transmit. And at any given point of time, you can only observe one sensor. And the source at each sensor is kind of correlated. So xi of t and xj of t are correlated. How are they correlated? We specify a very specific model. So xi of t plus 1 is xi of t plus Gaussian noise, wi of t. But across dimensions I and j, the way it works is that if I write down this in a vector equation, x of t plus 1 vector is x of t plus w of t, where w of t is a multivariate Gaussian with mean 0 and covariance matrix q. And this covariance matrix q is non-diagonal. If this covariance matrix q is diagonal, then everything is independent. But if the covariance q is non-diagonal, then there is correlation between I and j for each I and j, depending on however you define it. And so if someone tells me this covariance matrix, my goal will now be, I have this m-dimensional process, a Gaussian random walk, with correlated dimensions. I can only observe one dimension at a time. What I need to design is A, a scheduling policy, and B, an estimator at the base station that uses the correlation structure, basically Q matrix and the scheduling policy, to estimate what my current state is going to be given all my past information. So these are the two things that I need to do. And my goal in all of this will be to minimize monitoring error. I will not minimize age of information. My goal is to just say, I have an estimate x hat of t. My true state is x of t. I define x hat minus xt whole square. And I want to minimize that subject summed over all time. So a slightly different problem. It directly tries to tackle monitoring error rather than age of information. rather surprisingly, age of information still falls in. So we maintain this state x hat of t using some estimator. We haven't designed it yet. We define the expected error, and our goal is to minimize this expected error summed over all time. Yes.
Sorry, so age of information was just it was oblivious of what the actual information was.
Yes.
It would just say these are some packets and we know how to handle them.
Yes.
Here we are saying no, let's just give up the process.
Yeah, we are establishing a specific process, and that's why we can define the error and compute the error.
But did you also say that this will also tell you something about general abstract age of
No. So what this will tell you is, so if this Q was diagonal, this problem actually becomes exactly the same as weighted age minimization. Basically, the weights will be the diagonal elements of this Q matrix. The larger your variance, the more quickly your dimension changes. That will be your weight. This expected error will grow linearly with how long it has been since you last observed that dimension, which is age of information. The problem is if this matrix is non-diagonal, then this does not look like weighted age. So the error is slightly different from age. So how do we solve the problem when this matrix is non-diagonal is the question that we ask. And so our goal is to minimize the time average error, which is this metric, basically. Summed over all dimensions, summed over all time, take times t goes to infinity. So we set up our optimization problem. Phi of t is our scheduling policy. Eta t is our estimate. So we will start describing our constraints. So our system dynamic is xt plus 1 is xt plus noise. Yt is basically the measurement or the observation we make at time t, which is xt and the dimension that you observe at time t, which is phi t. Phi t basically belongs to 1 to n because you can only observe one dimension at a time. That's my interference constraint. And x hat of t is the estimator that I have created from all the past observations that I have. So yt minus 1 up to y1. And it's not clear what the optimal estimator is going to be right now, because this is kind of a strange correlated setting with time varying observations. So what we will show is that let's assume that the class of scheduling policies that we are limited to are oblivious to the actual state. So you can't observe the state x of t to decide when to make scheduling decisions. You know age of information, so you know how long it has been since you observed each state, but you can't decide, oh, the current state is x in this dimension, it is large, or my error in this particular dimension is large and my error in this particular dimension is low. So I can use that to make a policy decision, because the base station will not know the actual state because it has not sampled the actual state. The sources will, the base station will not. And so we assume that our class of scheduling policies is oblivious to x of t. You can use the past, but you can't use the current state. Given that, we are able to prove this separability lemma. For oblivious scheduling policies, the optimal estimator is going to be the Kalman filter. So, and you can design the Kalman filter for this linear time varying system because your observations are actually time varying and not just one fixed dimension or some linear subset. And you can design this Kalman filter and you can design the optimal estimator. Given any specific scheduling sequence, you will get a particular iteration of the Kalman filter, which will basically give you a system of linear equations that you keep iterating over in each time slot. So that gives yes.
Can you explain the
Yeah, I will do it.
good. Okay, so what is the oblivious scheduling policy?
Yeah. So the oblivious scheduling policy, think of any policy that is stationary randomized, that is oblivious because it does not depend on state clearly. Any policy that uses any kind of network state or any kind of age of information or throughput information. How long it has been since you last transmitted? How many times did you transmit in the past 10 time slots? How many times have you transmitted for the last all of time that has passed?
So any causal policy is
any causal policy that does not depend on x of t.
okay. Right.
So any kind of policy that cannot access the state itself. Because if you access the state itself, then you would want to design a policy that says, oh, my error in this dimension is low. I don't need to observe that dimension. My error in this dimension is high.
So simply sigma algebra generated by the observer. That's it.
Sorry?
It is the policy that depends on the sigma algebra generated by the observer.
Yes.
That's okay.
This is stopping the anything also because the phi
XT is not observable. At the base station, XT is not observable. You have past observations. You can do x hat of t, but you don't have XT. You don't have access to XT at the base station.
Because you're trying to estimate x.
So you'll have y1, y2, yt minus 1, yt, and x hat of t. X hat of t is fine. You can't use XT.
But you can say that I haven't queried this particular source in a while, so now
Yes.
that is possible.
That is precisely the kind of policies that we will have, because that then becomes an age policy. Yes. So, clear on oblivious? Okay.
So Q is no.
Yeah, Q is known. We assume that you know the correlation structure. Yes.
Okay.
So, equivalently, this problem can actually be reformulated once you have this Kalman filter realization to something that just minimizes what looks like the diagonal elements of the Kalman matrix, because the Kalman matrix diagonal elements are actually the monitoring covariance error at any given point of time.
Like the Kalman filter, given the x hats gives you y. Sorry, given the y's gives you x hat.
Yes.
Okay.
It's the conditional expectation.
Yeah, exactly. Yes. And so we are basically reformulating the original problem, which was the error problem, to now something that just involves the Kalman recursion. So a Kalman recursion looks something like this, where e pi of t is a one m-dimensional vector that is 1 at the location at which you're doing the scheduling and zeros everywhere else. And this is what the Kalman recursion looks like for that particular scheduling choice at time t. If you go through the paper, you can establish exactly why this is the equation. It's not really important why that is the equation, but p of t plus 1 at any given point of time t plus 1 is the covariance matrix between x minus x hat, the vector. And so the diagonal element of that is going to give you the error, because it gives you x minus x hat expectation squared. And so if you give the trace of that matrix, that is your total error between your estimate and your actual state. And if you sum up this trace of this matrix P over time, that is the thing that you want to minimize. So this is what we're trying to do. We are basically trying to minimize this trace of this matrix. The QIIs are just so that they help us with analysis. And our scheduling constraint is the same still. You can only observe one at a time. And again, this problem is basically a dynamic programming in m dimensions and an infinite time horizon with this strange, complicated Kalman recursion. Hard to solve. We actually don't know how to solve this optimally. And so what we will try to do is we will try to establish some kind of upper and lower bounds for this objective function given any kind of oblivious scheduling rule, that they will start to look like the age of information. And once you have this age of information upper and lower bounds, then all you need to do is optimize the lower and upper bounds. And if you know how to do optimization of those upper bounds and lower bounds efficiently, then you can solve this problem reasonably efficiently. And so that is what we'll try to do. So the main result is that our monitoring error is upper bounded by this age of information upper bound, which states that at any given point of time t, my error in dimension I is upper bounded by QII, which is my variance in dimension I, times the age of information in dimension I. So what is the worst case error that I could have? Let's say that there was no gain that I got from correlation. Then in each time slot, the expected error I had is just the variance of the noise. So if I know that my source was at value 0 at the current time, if I don't observe it in the next time slot, the total error will just be 0 plus the variance in this dimension. In the next time slot, it will be 0 plus the variance plus the variance. So it just keeps growing linearly in terms of the error variance. And so this is kind of the worst case upper bound, no benefit of correlation. The lower bound is what we call the optimistic benefit of correlation, where we assume you can extract all the information that you could have extracted from all the other dimensions in some kind of optimistic way. And that is what this QII tilde is, which I haven't really defined. Turns out that the lower bound also scales with the age of information as long as you put the correct weight here, which accounts for the benefit of correlation. So we'll try to go over that. So if there was no correlation, this is the worst case error, as I just established. And basically what this tries to do is it tries to split the covariance matrix Q into two parts, which is QII, which is the variance in your own dimension, Q minus I, which is all the parts that you don't know, and then QI transpose and QI, which is kind of the covariance between you and all the other dimensions that you could have observed. And what we try to do is basically understand how much information could you have gained from all of these other sources. And if let's say you could add all of that up, so you could observe all of the other sources instead of just one, how much information could you have gained? That kind of scales as QII tilde, which is what we have defined here. As long as Q is nice and invertible, you can compute this and it will be non-zero, so the lower bound is a non-trivial lower bound. And then this also scales as a function of age of information. So the upper bound is tight if there is no correlation. the lower bound is not tight because we are assuming this kind of very optimistic benefit of correlation where you're saying that you can observe every other source except yourself and account for its advantage through the Kalman filter. From these bounds, we can just say immediately, because they are per time slot and per dimension, you can sum up over each dimension, you can sum up over each time instant, that this original cost function is upper bounded by a function that is just a weighted sum of age, and lower bounded by another weighted sum of age where the weights are slightly different. Which means that you can optimize either the upper or lower bound. And these problems are much easier to solve than this middle problem, which is much harder to solve. And so what we'll do now is basically analyze the upper and lower bounds using our standard max weight style techniques. So one possible policy that you could try to solve for is basically choose the source that has the maximum expected error at any given point of time. Because you know the expected error, you don't know the exact error because we are restricting to oblivious policies. But given the entire past history, you can run the Kalman recursion. You know, given the Kalman recursion, what the expected error is going to be. It will turn out to be PII divided by square root of QII. And you can just choose that particular source. Turns out that's pretty good policy. The other one is choose the source that has the maximum weighted age, which is QII times HI squared. So if you recall from section 1, that was weight times age squared. This is weight times age squared, where weight is just your variance in your dimension. What we show is that both of these policies have nice performance guarantees. The performance guarantees, what you need to do is just ignore this big fraction. It's a constant. It does not scale with the number of, or the size, or the dimension of your problem. All of this does not depend on M. It's just a big constant. In cases where the matrix is completely diagonal, this will actually reduce to 2 or 4, which is the constant factor guarantee that you will see in the uncorrelated setting. Because we know that for the uncorrelated setting, this policy has a performance factor of 2. This kind of factor will boil down to 2, and you'll re-obtain the same result that we had in section 1. So this is kind of the main claim in our paper, which is that under this very specific correlation structure, which is Gaussian random walks, and oblivious scheduling policies, you can separate optimal estimation and optimal scheduling. Optimal estimation is a well-known thing that we know how to do. And optimal scheduling under the Kalman filter of estimation is actually going to be something that we also know very well. It's just going to be max weight age or something like max weight error. And both of these have nice performance guarantees that can be proved using standard Lyapunov techniques. And so what we are showing is that even though we think that, oh, correlation, age of information is probably not the right technique to try to solve this, for specific models, it tends to work well. And yeah, the main way of proving this is basically coming up with the appropriate Lyapunov function, using analysis to prove that this error does not grow too large. And if you have worked with Lyapunov functions, then you'll know that it's just, at some point, it's just a bunch of inequalities that need to propagate over time. And once things cancel out correctly, you will be done. And some nice simulation results. So we start with this correlation matrix, which is 1 along the diagonals and rows everywhere else, where rho is 0.8. So it is reasonably high correlation, right? And we increase the number of sensors, and we look at all different policies. And what we're plotting, again, is a bunch of different performances. So on top is what we call the greedy policy. What the greedy policy does is simply schedule based either on age or error. But because you don't take correlation into account, all you can do is schedule the source with the highest age. And it will perform very, very poorly. The stationary randomized policy, because everything is uniform, will schedule each source with probability 1 over n. That also doesn't perform very well. It performs okay, but surprisingly better than the greedy policy, which is kind of non-intuitive, especially in the age setting, because you will always think that a greedy policy in age would perform better than the stationary randomized policy. Here, for monitoring error, in this particular correlated case, a stationary policy is actually better than the greedy policy because the greedy policy does not take into account any correlation structure. And then we look at our policies, which are the MW and the MEE, which is taking into account correlated error and age. So MWA is actually very, very good. MEE is even slightly better than that. And the green is our lower bound that we had constructed using the optimistic correlation. So of course, the green is not achievable by any policy because it breaks our resource constraint, because it says you can transmit all the other sources when your source is not available. but it kind of shows that this still grows linearly with the system size. So it's not a trivial lower bound. It's actually giving you something meaningful in terms of the benefit of correlation in this particular high correlation set. And that is why we are able to give constant factor performance guarantees compared to this green line. And that is kind of the core of, do we have time?
Do you have time?
Okay, cool. Yeah. Good. So that's section 2. Section 3 will be pretty quick. So,
In fact, your phone.
Look back.
Yes. I had set a timer, but yes, I did. Yes, I had set a 55-minute timer from 4 to 4:30. I didn't realize I had set it on my US phone. Okay, so that's the correlated problem. And then section 3 is where I'm going to talk about different kinds of update sizes. So we go back to our simple problem of weighted age. We are not worried about correlation. We are not worried about how these sources are evolving. We are not worried about any of that. All we say is that you want to minimize weighted age, subject to the fact that source 1 sends small updates, source 2 and source 3 send very large updates, and source n sends small updates. And you know these update sizes, and I'll call them L1, L2, L3, Ln. So you know these weights, you know these L1, L2 values. How do you design a scheduling policy given those parameters that still provides you A, constant factor performance guarantees, and B, handles these different update sizes? The first thing that you might ask, given this setting, is do we actually need to consider these update sizes, or is it already solved from the older paper? So what I'll answer is you do need to, and we'll go through a quick example in the next slide to show that. But first, I just want to establish the system model very, very clearly. So there are n sources. To transmit one full application level update for each source I, you need to send Li packets. To transmit one single packet, it takes 1 time slot. But to transmit an application level update from, let's say, source 1, it will take you, if L1 here is 1, 2, 3, 4, 5, it will take you 5 time slots. For each packet, a transmission from, let's say, source 1 will be successful with probability P1. So everything is at the packet level, not at the update level. Similarly, for scheduling, everything in terms of decision making is at the packet level, not the update level. So the base station, after transmission of each packet, can decide which source to hear from. So let's say source 1 right now transmits its first packet to the base station. At that point, the base station can decide, oh, I want to hear a partial packet from source 2. And then I want to hear a partial update, so 1 packet from source n. And then I go back to source 1 and I listen to the second packet. And then I go back to source 1 and listen to the third packet. And so you can interleave packets of the same single update between sources. And that's where we are really interested in doing scheduling. And so one of the things that we are interested in is asking, does interleaving actually help? And we have a very simple example to show that. So I will skip the AoI evolution. And what I want to show is there are 2 sources. One source sends updates that are of length 2. One source sends updates that are of length 100. A policy that does not switch between these 2 sources will basically send a source 1 packet that takes 2 time slots, followed by a source 2 packet that takes 100 time slots. And so the age of information basically grows something like this. The blue age of information is for source 1. The red age of information is for source 2. So basically, even the source 1 only takes 2 time slots to transmit. It will have to wait for 100 time slots every time source 2 transmits before it gets a chance to transmit again. That is the no switching policy. It's pretty bad.
No, but the frequency at which source 1 will transmit will be much higher compared to, just think of SRPT, right? You will prefer packets with shorter time.
Yes.
So they won't be exactly periodically done every switching between them uniformly.
So that's what we're trying to, that's exactly what we're trying to say, right? A good policy would do something like switching. The policy that I described is no switching. It is saying source 1 will transmit its entire update, then source 2 will transmit its entire update, then source 1 will transmit, then source 2 will transmit. So at any given point in time, because each packet takes 1 time slot, they'll have the same age, source 1 and source 2 time average, which is bad because source 1 can actually have much better age if it can just interleave its packets in between a source 2 transmission. And so that's what we show. So the no switching policy is when source 1 and source 2 just transmit entire updates without switching. The switching twice policy is basically that between a source 2 packet, source 1 gets to transmit twice in the middle. It gets to transmit at 33, it gets to transmit at 66.
So you don't have to really use the middle. If like the larger packet is transmitted once, you can potentially transmit 10 short.
Yes, you can do that as well.
You necessarily don't have to break larger packets into smaller packets.
So any policy in this particular case that is no switching will not really beat this kind of uniform age, roughly.
At the end of
Over a long enough time horizon.
So
Yeah. Because the way age of information is constructed, it won't really help. If you, let's say you've transmitted lots of repeated source 1 packets followed by one long source 2 packet, yeah, then it doesn't really help. So, and then what we show is that this switching 10 times is when you're transmitting a source 2 packet, but within that source 2 packet, after every 10 packets, you transmit the source 1 update. And so you interleave this every 10 time slots. That is much better for average age than all these other kind of switching policies.
But this does require can require significantly more memory at the source.
It can require significantly more memory. It can require significantly more signaling overhead because you're doing signaling at a packet level instead of an update level. Of course, so there are more overheads, which we don't account for in this model. We're assuming that you have this system where you're actually doing this at the packet level, and someone has told you that the transmissions are going to be either large or small, and you know these transmission sizes. How do you optimally schedule them to minimize age of information? And that was a problem that had kind of remained open because earlier analysis had assumed that everyone just sends one packet. And so when you're trying to transmit large or small updates and mixtures of them, you don't really know what is the best way to interleave them properly. So that is what we will try to solve. And the main issue here is that earlier analysis tries to establish a Lyapunov function and then show that, okay, in each time slot, you compute the drift in this Lyapunov function, find the decision that minimizes this drift. And the decision that minimizes the drift, keeps your system state small, is going to be a good decision and will give you some nice performance back. The problem here is that when all of the sources have large packet lengths, then at any given point of time, any decision you make is actually not going to change the age of information. And if your one slot age of information is not going to change, your Lyapunov drift for every system action that you take is just going to be 0. So you can't make decisions based on Lyapunov drift, then you're kind of stuck both in decision making and analysis. So how do you adjust your system model to reflect this kind of long-term decision making with a single time slot Lyapunov function is slightly tricky. And that's what we do. So we basically redefine a more interesting Lyapunov function where we have 3 terms. The first one is waiting time, which is basically composed of age of information and how many packets have you already kind of transmitted. And the second term is kind of how many packets you have transmitted, how many packets you have left. And the third term is throughput depth, which basically tries to ensure that you don't starve any particular source at any given point of time. So basically what you want to do is define some kind of throughput target for each source. And you want to sum up all the possible time instants when you try to transmit for this source. If this kind of throughput depth starts growing linearly with time, then this term will start exploding. If the age of information starts exploding over time, then this term will start exploding. And if you, during the transmission of any particular update, stop transmitting for a very long time, then this service time kind of starts exploding. And so you want these 3 terms to interplay together with each other to ensure no starvation, information freshness, and the fact that once you have started transmitting, there's some pressure to keep transmitting. And not that you just stay silent so that other sources get to transmit during your duration. And combining these 3 together with the right weights, where beta and gamma are kind of parameters that you can choose, you can now do Lyapunov drift analysis over a single time slot and still provide performance guarantees. And so that is what we show. Again, ignore all of this. The main result is that our performance compared to the lower bound is going to be some constant factor rho. The constant factor rho depends on a whole host of factors. It depends on your weights. It depends on your packet lengths. It depends on your channel reliability. It depends on your throughput targets that you set. The most important thing to realize is that all of this does not scale with n, so this is a constant factor. And so what we show is that even with this new, slightly more complicated setting than we had started from in the first slide, if you recall, with different packet sizes, the same general approach works but you need to tune your Lyapunov function a bit more carefully to account for these packet sizes. And what we show is basically this kind of performance gear. Again, the green line is the greedy policy, which ignores all of this packet information. The pink line is the max weight H policy, but it assumes that the packet size is 1 for each update, which is incorrect. And then the blue circles and the blue squares are basically stationary randomized policies that we try to optimize for these kinds of packet sizes. What we show is that our new policy, the max weight policy with the new Lyapunov function, outperforms all of those and still has nice provable performance guarantees for very different kinds of packet sizes. Essentially, we have two different kinds of sources. One kind of source has reliable channels, but short packets. One kind of source has unreliable channels, but long packets. And depending on the ratio of the packet lengths, things can kind of change. We have some nice results on when switching can sometimes be optimal, when not switching can also be optimal. Those are kind of other extraneous results that we have in the paper. But the main result is that Lyapunov style analysis still works despite having different kinds of packet lengths. You can still use one slot Lyapunov drift. You just need to design your Lyapunov function a bit more carefully. And so the high-level conclusion of this talk is that scheduling for freshness in single-hop networks is fairly well studied at this point. It's been about a decade since people have been looking at this problem. There were a few interesting questions that we wanted to tackle that we felt had remained open. We have partial answers to those questions. The three important future directions that I see in this particular space are especially practical implementations with software-defined radios, especially for the CSMA work. More general correlation models and analysis. So we started with a very simple correlation model in section 2. But what happens if you want to go to something that is more general? And then going from monitoring error to network control. So going from something like an LTI system with Gaussian errors to going to something where you're trying to model actual robots moving around and trying to send updates, and you're trying to control these robots over a wireless channel. How do you find the right performance metric? Age of information is probably not the right thing if you want to do control. There's something probably more complicated. Can you show what the right metric is? And if you know what the right metric is, can you show how to optimize it? Those are interesting open questions. People have been working on them from different perspectives. And yeah, that's my view of current state of the art in single-hop wireless network age of information problems. So thank you for your time. Yes.
There's something basic in the large packet or small packet thing that I did,
Sure.
which is if it's like a video, which
Yes.
requires a lot of packets.
Yes,
I mean, let's say one video is 10 packets.
sure.
So, but the packets there's going to be some like they'll send the video for some time, and then maybe some of the packets will again shift to
Yes.
another source. But you will wait to finish a whole frame of video.
Yes. So the idea is that we have these updates. These updates are basically what I will call information units. So you can think of it as a frame of video, or you can think of it as a chunk of video. Normally they'll compress video in chunks. And so you're transmitting that entire chunk, however large that is. And then you're splitting your transmission opportunities for that entire chunk between other users, so that in between that chunk, some other users that are sending, say, position or something that is tiny can come in and just send it for a few milliseconds, and then you get to transmit again your big frame.
But by then there would have been other frames that.
Yeah, so you will have a queue there. The idea is that in age of information, we always maintain just a single update queue. So if you're transmitting right now, right, and let's say that I transmitted the first packet of my frame, and now I'm waiting for source 2 to transmit. In the meantime, a new frame came in. That frame will get lost. I won't actually transmit it, because now I have started transmitting this. I will have to finish transmitting it. And once I've finished transmitting it, then only the new frame will come in. So there is some transmission and opportunity cost in age of information to doing it. And the Lyapunov function kind of takes care of that by optimizing for that. And we assume that this is only just one update length queue always. So anytime a new frame is generated here, if you're not transmitting, this will immediately get replaced. So the old one will get thrown out, the new one will come in. If you are transmitting, the old one will be kept and the new one will be thrown out, which is a loss in the opportunity cost.
Do any of these things do any there's like whatever update losses, right? There's some.
Yeah, so we don't care about
Data
loss
loss.
because we are optimizing for age of information. So the idea is that think about like video conferencing. If a frame is lost, it has no value, so you just throw it out.
Oh.
Yeah. Even if it was fresher, because you have just thrown it out, you have thrown it out. It does not lead to worse performance just because of the loss. It only leads to worse performance because it was fresher and it could have been transmitted. Other questions?
All right, if there are no questions, let's thank the speaker, right? Costly transmission or budgeted transmission cannot be this so many times.
Yeah, I think
We'll see.
that can be a more into finite time. If you have a finite time problem and you have these budget on,
Let's say within any sliding window, you can only do it so many times.
yeah, then yeah, you can formulate it as a dynamic program to kind of scale with the length of the window and what your budget is, kind of start looking like something like.
I think we're going to reduce fact variations. Some of the techniques that use would be good.
Lyapunov drift won't really help because the nice thing with Lyapunov drift is you have this like infinite time horizon. So you start summing up over things and you say that, okay, I have some performance bound over infinite time.
Yes,
And so you want to give finite time guarantees. Lyapunov drift is usually not the best technique. So,
they're like a simpler dynamic program might be able to work or something.
yes, but what you typically would want to do is have like fairly large window sizes, and then the dynamic program would be hard to compute. So what you might be able to do is still take there is some nice analysis from Age of Information folks under reliable channels, where you start studying periodic policies, because you know that some kind of periodic policy is going to be up. And then once you start limiting to that, and then start or like approximately periodic or approximately cyclic policies where you define approximate in some way. And then you start looking at patterns in there, what is kind of the fundamental limits of what periodic policies use. So there's a bunch of results on that. And that will work pretty well for window sizes. So there's a bunch of this is from Ness Strauss group and Thomas Wu's group in Ohio State and Virginia Tech. They have a bunch of work on this. I think Chengzhang Li is the guy who's doing this. You need to look up the paper. I can
Check with Rahul.
Oh yeah, this is But there will be a series of books.
Yeah, that's.
Okay, thanks. That was a nice talk.
Okay, thank you. Yeah.
Look, except for your preemption, why actually solve the same problem? You're allowing preemption, we didn't allow preemption.
Okay.
So each packet,
Yeah.
essentially, what we did was a different way of modeling the same thing. Different sources essentially have different delay profiles for the packets to get to. Similarly, if you break it up, we will restart, so there's no preemption. So what you're allowing is essentially preemption to the restart.
Yeah.
You didn't allow that. So if
Okay.
you start a packet, it's long.
Yeah. You.
And if you want to preempt it, it's okay, but then that packet has to be completely retransmitted. You can't start from where you start.
I see.
Then you get 4 optimal answer
Okay.
and without going.
That's the long TOI paper. I think I
Yes.
read that. Yeah.
Super 50.
Yeah. I remember. I think I read it.
So that's so. I see the utility of the way you're doing things.
The utility mostly came from Igor was actually implementing some of this, and I was also trying to do this for
I was
robotics.
just trying to see.
And then it actually helped, like, this is
How
going to happen in a real system.
we will include that in our setting in whatever.
Okay.
Because anyway, we're assuming they're all memoryless. So we actually allowed even non exponential distribution. So arbitrary distribution also works.
Okay. We assume like deterministic packet size.
It only depends on the ratio of the second moment to the first moment squared.
Okay.
So it's 4 plus something of that type.
Okay.
And for the exponential, it turns out to be 4. So it's 3 plus something, and then
Okay.
for exponential, it turns out to be. But because it is exponential, preemption should not matter. So even if I were to abandon the packet, I can restart all over. The residual remaining time is the same. So it really actually doesn't matter.
Okay.
So even if I were to include that feature.
Yeah. Yeah. For us, memory is very important because it's all deterministic.
Correct.
Yeah.
So at least in the experiential case, what it is sufficient. And yeah, yes. You could handle very general inputs as well. Input arrival processes could be completely different.
I see.
His large packet and small packet is modeled by the total amount of time it takes a packet to get.
Yeah.
Each so take a different deal.
I see.
So let's see it. So that is, yeah, so that's how we solve that problem. Except that we allow you this preemption that in between I can stop the
I see.
packet and insert a small packet.
Mm.
For us, if you stop it, then you stop it. Then you either restart or you're running. That's the only difference.
Do you assume that packets are available whenever you want to? If
No,
okay, so that's what we assume.
it's also arriving.
Okay, we
using
don't
plastic
assume.
process.
Yeah,
So there's no generator there. So all sorts of,
we do a generator for
so
simple.
except for this one particular thing, is quite general.
Mhm.
That's a, I remember it's a very bad paper.
Yeah, I will look at it again. I think there is similarities. Yeah.
Because the analysis is not as difficult, but actually doesn't.
So you don't Lyapunov.
Yeah, you know, without that. It's more, this could tell them, rather than something that tell them.
Order is
That's the reason. That, that is that. Yeah. You want some snack? There's some someone like.
Giant from us.
So now I
Take it in from me. That question I'm very intrigued. So what you said is the following.
It will stop
But correlated.
Yes,
The correlated thing is very interesting and forget